So very, very warm welcome from Bangkok. We are having now the fourth webinar that has been the initiative of the framework of Mother Declaration on the control and prevention of the air pollution and its likely transboundary effects for South Asia, or in the short name as Mother Declaration, as we know, that it was adopted since the 7th Governing Council of South Asia Cooperative Environment Program, or SACEP, that we today am Vanessa Surapipit from this Asian Institute of Technology at the Regional Resource Center for Asia and the Pacific. So in collaboration with SACEP, we will continue with this program in webinar series that has been initiated by the Director General of SACEP, and also the member countries has kickstart together with this webinar since March. So this is the fourth month that we have had every last Monday of the month. So in this month, we are very fortunate to have a chance to invite distinguished speakers from not only from South Asia, but we have one speaker as far as Europe in Sweden. So I'm very, very happy to welcome you all today to this webinar in the concept that we coined out as the quality management, science and investment for sustainable development in the Mother Declaration member countries. So the topic today will be about what and why super pollutants. This is the discussion about the long-term monitoring in South Asia. So we schedule at the same time every last Monday, and now is the time. So let me just review briefly only about what is the Mother Declaration that has kickstarted in 1998 after a roundtable of the policy dialogue held by the United Nations Environment Program and the Stockholm Environment ACI, UNEP and ACI met at Asian Institute of Technology here, where I am now in Bangkok since 1998. And afterwards, they have representatives from the Ministry of Environment from all the South Asian countries in the meeting. So they have agreed to initiate this intergovernmental network involving Bangladesh, Bhutan, India, Iran, the Republic of Maldives, and Nepal, Pakistan, and Sri Lanka. So it's we have actually altogether 8 member countries, and actively most of them in South Asia. So the declaration has emphasized the need for countries to carry forward the studies and programs on air pollution in each of their own country, and also to support at this moment very critical issues regarding the atmospheric environment. So the Mother Declaration has been running since, as mentioned, 1998, and until now there has been a discussion last year to have this webinar after our discussion at the Ambition to Action meeting in Bangkok last year. So we have agreed that we should have a continued discussion, and so that in a near future, the intergovernmental meeting of Mother Declaration is coming up, and SACEP has initiated that the intergovernmental meeting coming up just by early next month. So this topic for this webinar about what and why super pollutants will therefore be very, very significant. So I hope that everyone who is now gradually joining us will look forward to hear about how the monitoring of super pollutants can be carried out in South Asia, that and what is super pollutants. And at the moment, we will have the speakers to describe about it. Today we have 5 three speakers, including these five, then and three speakers, main speaker, and one person, distinguished guest, to give the concluding remarks. So we start off today with Professor Örjan Gustafsson from the Stockholm University in Sweden, who will describe to us about what are the superpollutants and their roles in the climate system of South Asia. So in this respect, Professor Örjan Gustafsson has done a lot of research within the region itself, and not only in the region of South Asia. He has extensive research collaboration, and in particular that regarding climate and air pollution. I will introduce in more detail afterwards, and he's here. And next speaker for today is also here with us already. We have a program a little bit to have the second speaker as Professor Abdul Salam, who is actually now the vice. He's now sharing within for our the University of Dhaka, who is now the Pro-Vice Chancellor of the University of Dhaka. Previously, he was a Dean of the Faculty of Science at the University of Dhaka itself. So he will talk about the long-term monitoring and the observation at Bangladesh at the Climate Observatory in Bhopal, and so that how the superpollutants are being monitored in North Bengal and beyond that. And the last speaker, but not least, is Dr. Krishnakant Budawan from the Maldives Climate Observatory at Hanimadu. Actually, he has been serving as a research associate professor at the Divesha Center for Climate Change and Indian Institute of Science in Bengaluru in India. But he also a very key person as a resident scientist at MCOH, the Maldives Climate Observatory. So we will hear from him regarding the topic of the long-term monitoring out there at MCOH. So it will indicate about the status of the superpollutants about over Indian Ocean. And afterwards, we will have the closing final remarks from Ms. Yoo Jong Kim from the United Nations Environment Program. Actually, Ms. Yoo Jong Kim has been serving as a senior program management officer for UNEP based in Bangkok. So she has been a very busy person working, focusing a lot on environmental science and policy interface in the region. So just a brief introduction to the speakers before I will bring everyone into the actual content of the today program. Can I ask the speakers to be for a moment of our group picture. Are you ready? Okay. So, okay, just the technical team, please help me. Then we smile. Can you count also? Is that done? Okay, I think that should be done. All right. Okay, thank you so much. So I think without wasting much time, I will then move on to the first speaker. So let us bring up only Professor Örjan Gustafsson, who has dedicated his time today out of the morning hours in Sweden. He served as the committee for this the Royal Swedish Academy of Science regarding the Nobel Prize chemistry, and actually he has been working as a professor in biogeochemistry at the Department of Environmental Science and Bolin Center for Climate Research in Stockholm University, and he chaired the board of directors on Future Earth Global Hub. So a lot of long profile. I would not like to say too much at the moment. So you can also read in the chat box about his profile. So without wasting much time, I think everyone waiting to hear from Professor Orjan about what he please give us the light about what are the super pollutants and why we have to be worried about or think about, and what has been done as a long-term monitoring, at least for South Asia. I know that he has been doing a lot of research, not only in South Asia, but the focus at the moment very much relevant to the Mare Declaration region. So we are very happy to have him here today. So I pass on the microphone to Orjan, please. Thank you so much.
Thank you very much, Vanessa, for that very good framing of today's Mare Declaration webinar, and for the nice introduction. Can you confirm that you can see my first screen in full mode, presentation mode?
Yes, it is now. Good, yeah, full mode.
Thank you. And thank you very much for inviting me to this. I feel that Mare Declaration and SACEP is very well positioned for major contributions, which it has already is doing, but it can be expanded. It is a sister organization to the European air quality regime, which is called ClearTap, with its monitoring part called EMEP, and its addition of black carbon to that called in the Gothenburg Protocol, which is an addition afterwards. So Mare Declaration is set to do very important things. So I'm very happy about this re-injection of energy that you all are just now contributing to. So I'm going to share about bidecadal 20 years of observational constraints on the sources and effects of super pollutants, as we oftentimes call them now, short-lived climate forces, short-lived climate pollutants. And I also like to acknowledge here both Professors Abdus Salam and Professor Krishnakant Buddhavant. The three of us are long-term collaborators to building this infrastructure and making the science out of that. And then after the science, trying to make policy useful information extracted of that. So I'm showing here the NCO Hanamadu and the Bangladesh Climate Observatory Bola, that each of them will talk more about. And in the central map, you also see then a measure of integrated air pollution, the AOD parameter, showing how well positioned these are, the BCOB at the outflow of the highly polluted Indo-Gangetic Plain, thus serving as an ideal receptor observatory to pinpoint sources and effects from that, whereas MCOH in the northern Indian Ocean is strategically located with a large footprint uptake for an integrated picture of the air pollution and its climate effect over the greater South Asia. I want to start here with a couple of slides on why this matters. Already today's plus 1.2 degrees Celsius global average gives very large effects on both nature and humanity, as you know. For instance, with extreme weather affecting precipitation patterns, heat stress, and so on. This has also direct effects on human health. One of those is the wet bulb temperature, which is something that I'm very concerned about. I think we all should be. It is the combination of temperature and humidity when sweating is not enough. It does not work to keep the body temperature low. So it's a very dangerous situation. And the incidences of wet bulb temperatures, especially for South Asia, is increasing and will continue to do so. So it's urgent to reduce emissions of climate perturbing pollutants, super pollutants. So we need to do all we can to minimize climate overshoot. Climate overshoot being when we surpass the 1.5 and 2 degrees. Climate overshoot warming is also pushed over to the coming generations, including extreme heat. They will live their whole entire life through climate overshoot. And those of us that are already around, we are also experiencing it now and will do that for the rest of our lives. So we need to find ways to not only survive, but also to thrive in climate overshoot. And the most important thing is to do mitigation, but also to do adaptation to this, especially for the most climate vulnerable, it doesn't have so much climate resilience. With that as a backdrop, we go to this slide and what Vanessa talked about the WHO of climate pollutants or super pollutants. So this is the legacy IPCC forcing diagram, showing that CO2 is the single most important, but it also shows that there are many other important substances that affect the climate, and many of them are also affecting air quality. So there is oftentimes a double win or even a triple win in reducing their emissions. I want to highlight aerosols, sulfate, nitrate, and carbonaceous aerosols. As you see, they are net climate coolers. But that's not very good because they're affecting human health at the same time, so we have to reduce them. It means that when we are cleaning up air quality, it will heat up even more. So we risk having these heat effects. There are also very large uncertainties. They are very important. Look at the size of the error bars on the sulfur. Methane, absolutely central super pollutant. It's a short-lived and critical greenhouse gas. Over 60% comes from the tropics, it is believed. There are large uncertainties regarding its sources. And there are indications there is now enhanced releases due to climate warming from wetlands, waste, and agricultural sector. I highlight black carbon. Here in the IPCC assessment report number 6, it might not look very big, but that's a mistake to think about it in that way. There's a large error bar, and this is a global average. In regions, black carbon only stays in the atmosphere maybe for a week. In certain regions, such as South Asia, it has a much, much larger watt per square meter. I also want to mention CO, which is a very important short-lived climate pollutant or super pollutant as well. Here, I don't have time to talk about that. Let's start with black carbon. So in the AR6 to the left here, it is globally 0.2 plus minus 0.3. So it could be 0.5. It's a big effect. That's global. Regionally, such as in South Asia, much, much more important. But in the previous IPCC report, AR5, it was at 0.7 plus minus 0.4, so up to 1.1. And there is not a lot of good explanations why this has been taken down. But there is disagreement between models and observations. And I'll talk about that. Just for our knowledge, we think black carbon was confused in the AR6. For that reason, the senior editors of Nature commissioned to us, asked me to get a team together to review and assess the current state of knowledge with respect to black carbon. So we put this paper together called Atmospheric Black Carbon in the Climate System, with a large focus on South Asia. Look at the author list. There's a lot of South Asians involved here. More importantly, the author list included both people that are experts in observations, which is absolutely central, like Salam, Krishnakant, myself, and others, but also includes leading climate modelers, large-scale aerosol climate modelers, such as previous AR5 IPCC lead author Gunnar Myhre, Jos Lelyveld and Klaus Klingmüller from the Max Planck Institute of Chemistry in Germany. It also included the leading emission inventory specialist of the world, Qiang Zhang, who leads the leading Chinese emission inventory for black carbon, Chanda Venkataraman, who leads the corresponding leading emission inventory for black carbon for South Asia and India, Smog India, and C. Clement, who leads the one for Europe. So we got together and put this together. I'm going to share some of that with you. I also forgot on my front page to highlight the South Asian Pollution Experiment, SAPOX, which is a regional collaboration involving close colleagues in India, Bangladesh, the Maldives, and us that have been involved in the region for a long time. Funding from this assessment came from, very important, from the Black Carbon Program of the philanthropic Clean Air Fund, which is one evidence that black carbon is again in the limelight. South Asia is absolutely central to the development of the science and understanding of superpollutants, the linking of air pollution and climate change. It really got a big start through the Indian Ocean Experiment, INDO-X, in the late 1990s and early 2000s. A large number of scientists, led by Ramanathan, Crutzen, A.P. Mitra, and others, made studies and recognized that what was earlier thought about as an urban phenomena, air pollution, city, bad air, is actually spreading 1,000 kilometers over regional scale and have climate effects. This discovery transformed then into a program called the Atmospheric Brown Clouds, under the auspices of the United Nations Environment Programme, where humans played a very large and important role for well over a decade. We established permanent installations, such as the Maldives Climate Observatory Hanamadu, a similar one up in the Himalayas, and in similar one in the Southeast Yellow Sea for the corresponding outflow from East Asia, with then Bangladesh Climate Observatory Bola also added. That has then since transformed into SAPOX, the South Asian Pollution Experiment, which is an informal but very productive collaboration in the region. It should generate a lot of knowledge on superpollutants and their policy knowledge. So here in South Asia is where it was discovered that urban-like air pollution spreads over regional scale and have an impact on climate and health. Major discovery is that black carbon from incomplete combustion of fossil fuel and biomass is abundant and important, but also other aerosols, light-absorbing brown carbon, and methane, CO, ozone, and so on. It's also these science teams that coined the concept of short-lived climate forces, short-lived climate pollutants, sometimes now called superpollutants. And to show that it has really had a big effect on policy too, the SSCPs are now its own chapter in IPCC report, and they exist as provisions for national emission reductions in the UNFCCC climate treaty, the Paris Treaty. Mali Declaration certainly plays a role here and can play an increasingly large role as well. So this is an area, the superpollutants, with South Asia being central both for knowledge generation and for mitigation action. It's an area where we really are able to package the science in a way that it becomes policy useful to act to fight short-lived climate pollutants. One example is the Climate and Clean Air Coalition, which is managed to reduce short-lived climate pollutants. It was created by Bangladesh and Sweden as two of the original members, startup members. What we really need is long-term atmospheric receptor observatories. It's not enough with a 3 months or 3-year study. We need longer term because of the chaotic nature of climate and air quality over large scales. We need that to advance on understanding the sources, the effects, and to also, for verification, to constrain how accurate are emission inventories that we rely on, and also then to guide mitigation efforts. So we invest towards reducing emissions from the most important sources. And here MCOH and BCOB play central roles for South Asia. I have a quote here, and I don't know who came up with it, but I think it's a good one. Think about it this way. Heavily investing in mitigating super pollutants without measuring the actual effect in the atmosphere is a little bit like going on a diet without stepping up on the balance and weighing oneself. No one would do that, right? We would all step up and see if it has an effect. Same thing, when we invest in society to mitigate super pollutants, we need observatories to measure that it actually has an effect in the composition of the atmosphere. That's why we need observatories. Okay, back to the review article. Constraints on the atmospheric life cycle of black carbon. Black carbon is very complicated. It is the most complicated climate perturbing substance and super pollutant. It has so many different sources, and then when it's emitted into the atmosphere, it mixes with many other components, it distributes, it interacts with cloud formation, it interacts with solar radiation, and it matters a lot whether it's below, inside, or above clouds. And it matters where it deposits to, how large its effect is. So it is a complicated matter scientifically, but we know certainly well much more than what we need to act on it. Further progress is likely to come from intensified collaboration, I believe, between observations, emission inventory specialists, and the modeling community. And we will continuously provide policy useful scientific underpinning. So what's the problem in the field of science? Well, there is a systematic gap between model predictions and observations of black carbon, here illustrated by a parameter we call aerosol absorption optical depth. It's through the atmospheric column, the absorption of solar light, which happens largely but not exclusively by black carbon aerosols. So what I'm showing here is both model and observations. In the background grid here, the blue and white, is the model predicted BCAAOD by a large global aerosol climate model. And the circles is the same parameter, AAOD, the scale bar is at the bottom here, from measurements. So if the models would agree with observations, we wouldn't see the circles because they would have the same color as the background. But you see this is systematically higher value in the observations, in the white and reddish, whereas the models is in the blue and light white. Okay, so this is systematic factor of 2 to 3 underestimation model by the columnar integrated black carbon. So in the current review article that just came out a few months ago in Nature Reviews, we repeated this exercise. And to make a long story short, there hasn't unfortunately been any improvement over the decade. There is still a factor of 2 lower estimate of AAOD from black carbon in models than in observations. Why is it the fact that models are underestimating black carbon, AAOD, and also the direct aerosol radiative effect of black carbon, which I haven't shown you, and I will not show you, but it is the same underestimate there. Well, the reasons are, hypotheses are, that we're underestimating the ability of black carbon to absorb solar light, parameter we call mass absorption coefficient, MAC, and the effect of mixing with other components that may enhance black carbon absorption during long-range transport. It could also be because we're underestimating atmospheric residence time of black carbon aerosols. If it stays longer in the atmosphere, it has a bigger total effect. We might underestimate light-absorbing organic carbon aerosols, brown carbon. We might underestimate the total black carbon emissions. It's very difficult for all these small-scale and open combustion systems. It's well recognized to be a challenge. It could also be that we're in the emission inventories have an incorrect source attribution between fossil combustion and biomass combustion. And we don't quite understand the vertical distribution of black carbon. So I'm going to share some assessments of a few of these parameters. We don't have time for more. I'm going to start with the mass absorption coefficient, the ability of ambient black carbon out there in the atmosphere to absorb solar light and thus heat the atmosphere. So we actually scrutinized well over 300 studies, and after our censoring for quality assurance, we were down to 151 studies. And these we have summed regionally here in the purple bars for South Asia here. It's above 12. And we compare that with the legacy MAC value in Bond and Bergström, cited well over 5,000 times in the scientific literature and using climate models, which puts the MAC at 7.5. Those measurements, those data were based on a lot of laboratory studies and close to source locations, such as road tunnels and so on, in the US, in Europe and so on. When we look here at the global observations in the atmosphere, the value is more close to 12. So this is one reason, likely, why models are underestimating the climate effect of black carbon. We also find globally that this enhancement due to coating is around 1.6. So now we have a follow-up to the review article underway, where we compare this up-to-date ambient MAC database observations with a wider set of AeroCom models. So I look forward to see that study happen. Second thing is residence time. And here Krishna Buddhavan, together with Klaus Klingmüller at the Max Planck Institute for Chemistry, took the lead for that part of the assessment. And to the left here, we're seeing, we're comparing here MERA2 reanalysis. There is a mixture of observations from satellites and modeling. And here is the multi-year deposition flux estimates from observations, and in the circles are observations. And we find that in the model, the MERA2, it predicts more deposition than what we find in the observations. Similarly, when we estimated residence times from observations using Jung-Jobson statistical relationship, compare that with the MERA2 estimates, the model gives lower residence time of the shorter residence time of black carbon than observations. That could also help explain the underestimated black carbon in models. And also when you just look at the model predictions from MERA2 of ground-based black carbon, it's okay for Europe, but it underestimates black carbon in South Asia and elsewhere relative to observations. Observations are central. That's those two factors. And the third and final one I'm going to talk about is the emission inventories of black carbon. So we worked with 6 of the leading emission inventories in the world. The CETS, the Community Emission Database System, which is one used in the IPCC, in this modeling studies, CMIP6, that went into the IPCC AR6. The Eclipse from Europe, EDGAR, RIAS, led out of Japan, but for global. SMOG India, led out of IIT Bombay, and MAKE, led out of Tsinghua University in Beijing. So we're showing this for India, China, and world. We can focus just on India. So here we have on the x-axis how much each inventory suggests black carbon to be emitted. So for India, it goes something from 650 to maybe 1600. So it's a factor of 2 to 3 range in what the emission inventory says how much black carbon is emitted. On the y-axis, it's what the emission inventory suggests how much comes from biomass burning. And the corollary is 1 minus biomass burning is a fraction of fossil on the right y-axis. So there's some range here too, from 35 to maybe 65% or so. So, but it's better than earlier into comparisons of emission inventories, but it still is a substantial range. Now, we have developed, starting in Maldives and in India, measured to do microscale radiocarbon dating, carbon-14 dating of the black carbon isolate of atmospheric aerosols. First paper back in 2009. And now there's over 50 such studies globally by our team and by others. So we're able to do that in situ carbon-14 source apportionment with carbon-14 between fossil, radiocarbon dead, and biomass burning, radiocarbon alive. And compare that with the predictions from CETS, the leading emission inventory used in IPCC, and GFED for vegetation fires. And we do that for different regions then. Sub-Saharan Africa, South Asia, East Asia, Europe, North America, and also in Tibet and Himalaya. What is the situation there? So by and large, there is quite good agreement in this source attribution between fossil and biomass, between observations and models. One exception is South Asia, where there is an offset, which we want to understand better. So more work needed for South Asia to attribute to the sources of black carbon. We note that there is a large difference in different regions. The fractions that come from biomass burning ranges from 93% in sub-Saharan Africa to about 50-50 in South Asia, to maybe just a quarter from biomass burning in East Asia. That also sets us up as a nice system to compare this to better understand black carbon. Now I'll switch gear here and look a little bit about, so how is the loading of black carbon over South Asia changing? We want to know that. Where are we? Anytime we emit an anthropogenic substance, it starts from low levels and then it oftentimes exponentially increases, reaches a plateau, and then decreases more slowly. So in North America, Europe, we bent that black carbon curve some decades ago. We actually removed a lot of aerosols, and this was very good for air quality. It's a success. It's also one reason why now we're having a lot of heating over Europe. China bent the curve about a decade ago. So let's see where we are in South Asia. So emission inventories, such as SEDS using IPCC, and arguably the best one for South Asia, Smog India, suggests increasing BC emissions up to the most recent reports, shown in these two lines of graphs. In the lower right here, we have the suggestion of black carbon loadings from CMIP 6 model into comparison project for AR6. And looking at the difference between the loadings of black carbon in the model from 2024 minus that in 2010. And we see then that it has decreased. It's green in China. It continues to decrease in Europe and North America. But for South Asia and in the Gangetic Plain, it has been increasing according to the model. So both emission inventories and models suggest increasing trends still for black carbon over South Asia and India. Let's contrast that with observations. So again, in the assessment, with many good colleagues, co-authors involved, we gathered all the available data of high quality that we could for different regions, including for South Asia that I've highlighted here. It's the gray symbols here, if you can make them up. I highlighted it here, both in rural environments and in urban environments. And we do a double normalization to get all the different records on the same scale. So we compare it with the first common year, set that equals to 1, and then do everything relative to that. And what we find, to make a long story short, is for South Asia that there is no evidence in observations of an increasing loading of black carbon that is suggested in emission inventories and in models. Observation says no increase. So there is a dichotomy there. So we go to the best observatory of them all for South Asia, the one with the largest footprint, integrating over many years the alpha from South Asia, the Maldives Climate Observatory in Hanamadu. And same thing here, as in the assessment. Here's a measure of the black carbon using a filometer, and it also shows no sign of increasing black carbon over the past 2 decades. Seems like South Asia and India have bent the curve of black carbon, reached the plateau, and it's poised to decrease if you just accelerate mitigation. So observations, in contrast to emission inventory models, there's that mitigation in South Asia is now bending the black carbon curve. It has plateaued. So the updated view of black carbon is that, first of all, BC is challenging, yet there is progress in our understanding on many parameters of black carbon, including loadings. South Asia is a frontier in these studies. Long-term observations is absolutely essential for verification and to provide science-based guidance for mitigation. South Asia seemed to have already peaked with black carbon, contrary to the general picture from emission inventories and models. Observations says South Asia has peaked in black carbon when we take all the information together. Emission inventories and models are underestimating the BC loadings and thus the BC effect. We want to work together. We are working together across observations, emission inventories and models to move the whole science field forward. The implication of that underestimate in models is that if we were to mitigate black carbon, it would in reality have a much larger positive effect than what we would expect from models. So a larger positive payback on mitigations to both public health and climate. I strongly encourage you to consider inclusion of black carbon in the Malé Declaration for dual benefits for public health and climate. This will be very similar to the European sister agreement, the CLEAR-TAP, which did not have black carbon from the beginning, but then add black carbon through this Gothenburg Protocol or amendment, you can call it. Similar thing could be done with Malé Declaration. Finally, in the end of my talk here, I'm going to talk about methane. Very important and absolutely key for near-term action and to avoid the largest climate overshoots is to decrease methane. So here we have the atmospheric methane curve. And the unfortunate thing is that methane keeps on increasing. We call it soaring. It's accelerating an increase despite the global methane mitigation programs. And actually the current levels of methane in the atmosphere is above those that would be consistent with the IPCC's 2-degree target. Another aspect of methane in the atmosphere is isotopic composition. First in blue here is again just the methane mixing ratio, but in red here is the delta carbon 13 of methane. So we don't need to understand much of these isotopes, what they are and how it works, but what it does is it indicates sources. Isotopes are different types of carbon atoms with different mass. So they change depending on how the methane was formed and how it's degraded. So it started to all of a sudden to decrease. And if you look at it in a longer perspective, delta carbon 13 of methane has been increased since the Industrial Revolution until a peak all of a sudden in the early 2000s, and then a shift in isotope composition globally, and the great isotope plunge. It says something about changing sources of methane. It says, in fact, I can explain to you later if anyone is interested, that there is an increase in biogenic sources relative to fossil sources behind this increase of methane. Anthropogenic, biogenic sources could be rice paddies, wastewater, and ruminants. Could also be enhancement of natural sources, tropical and boreal wetlands, and thawing permafrost in the Arctic and Himalaya Tibetan Plateau. Tropics, methane hotspot region, very important region, not the least South Asia. So we need to understand methane better for South Asia. It's been too few large studies. So we have at the Maldives and in Bangladesh measured methane continuously with laser spectrometry for many years now, and also we collected glass flasks to measure the isotopic composition, both for carbon atoms and the hydrogen atoms. Then we put that into something we call the dual isotope steady state model, DISM. It's an open system steady state model. It's constrained by isotopes. It's independent from common inverse and bottom-up approaches that both rely on emission inventories. We wanted to step away from that and provide a complementary approach. So I'm not going to get into the details of that. First, we need to understand what is this sort of fingerprint of methane from different sources in order to measure at the receptor observatories and then source a portion. So we went around and collected samples in rice paddies, from sewage and wastewater, from agricultural crop residue burning, and from ruminants in India and Bangladesh. And then we measured the carbon 13 and the hydrogen isotope of that and found that it was a little bit different in South Asia than in these global databases. It's very important because then we can use the South Asian source fingerprint when we do our source apportionment next. This is what is shown here. We don't need to get into the details, but in the upper left here, we see again here the sources that we have determined. This is a fingerprint from combustion, agricultural residue burning, wildfires. This is the isotopic fingerprint, source fingerprint of thermogenic, fuel exploitation, refineries, transport, and so on. Here is the source fingerprint from microbial sources of rice paddies, wetlands, landfills, and here from microbial from ruminants and termites and so on. And here is what we measured, BCUB and MCOH. So with that, we can then do a statistical modeling to apportion how much comes from each of these sources to the methane in these receptor observatories for IGBP and for the Greater South Asia. But let's start with what the model says. We have the bottom-up models based on emission inventories and atmospheric transport. And then we have top-down models based on satellites estimating methane. They're not really measuring, they're estimating with a lot of assumptions methane. And they're also including an a priori estimate of methane based on emission inventories. So they're not independent. But this is what they predict with how much comes from microbial, thermogenic, and combustion. Here is what we found during winter-long campaigns in Maldives and BCOB. So what we find, based on the DISM model and isotopic constraint on sources for South Asia, is that the emission inventory-driven models, they're overestimating microbial sources, 87 and 88 instead of 70 to 80. They also underestimated thermogenic and combustion sources, which we show is factor 2 to 3 larger than in the models, and factor 2 perhaps 1.5 for combustion. So those are important differences. If we want to understand methane emissions in South Asia, we got to take all approaches and not the least observations in the region to guide us. This model framework, the DSM, also is able to provide estimates of the methane sinks in South Asia. And atmospheric composition is different in South Asia than elsewhere. So what we're finding is that not only hydroxy radical, which is the by far most dominant methane sink, but also chlorine radical is important. It's actually 2 to 3 times more important in South Asia than the global average and what the models would have suggested. Key here are receptor observatories operating over long term with reasonable funding. And here Krishna Kant and Salam comes in as key players and our whole Sapwex team. BCOB and MCH are key assets as South Asia super pollutant observatories, and they're actually world unique. My colleague Ram Ramanathan, world famous atmospheric chemist, he oftentimes thinks of MCOH as for super pollutants, what Mauna Loa, Keeling's Mauna Loa was for CO2 once upon a time. Long-term time series of climate perturbing substances. Mitigating methane is cost-effective and co-benefits climate, human health, and food security alike. So my key point is that MCOH and BCOB are strategically located large footprint super observatories to advance observational constraints on super pollutants in South Asia. You want to, when you make decisions, you want to be able to lean on solid science, and that's provided by this observatory. And it provides policy useful applied science. South Asia continues to be the arena for progress in understanding and I think now also action on short-lived climate pollutants, super pollutants. And I think it will be the increasingly most important arena globally for studies of super pollutants. We have some large footprint observatories. We need more, but these are key ones with a long time series. To provide constraints to verify and guide mitigation efforts of multiple super pollutants. We know that black carbon is a challenge in many ways, scientifically, also policy-wise, but reducing it has huge co-benefits for both health and climate. We know that methane is soaring, and we need to advance on pinning down sources, and we need to do that on a regional basis. So more work on that. Mali Declaration is a very important framework. It's an opportunity for action for South Asia. Here we have science to guide and catalyze practical solutions. BC and methane mitigation are low-hanging fruits and should be in focus, because fighting climate change is both a sprint and a marathon. We first need to win the sprint to 2030. There is a need for speed, but we're about to bend the curve. Thank you for your attention.
Okay, thank you so much. Professor Origen Gustafsson has a very clear message telling us how the long-term monitoring in South Asia at his huge research team has been indicating for us. This is a very, very good, clear conclusion. So I'm sorry I forgot to mention to everyone that you are welcome to actually send in the questions anytime, actually, during the presentation. So to save the time for that. But at the moment, if anyone want to send in a question, you are more than welcome to really type in here. Or you can do it now. I don't yet see any particular question at the moment. But of course, I think there would be certainly a number of questions, but I want to emphasize also that for all the participants, we will share recording, but of course, please make sure we will not share some slides that has been mentioned that is not yet published. So I feel grateful and obliged to the fact that Professor Gustafsson has already telling us about the latest research that going to be published, and this sending a very clear message also. Actually, before the webinar, we have some question, but we would like to come back to that to save the time, because I think one of the speaker, like the next speaker, Abdul Salam, he has to leave actually before the end. So does everyone join me to thanks again, and I hope Origen can stay with us till the end. Can you? Okay, that's great. Okay, so thank you so much, and I will move on to Professor Abdul Salam to tell us the story of the observatory there in Bangladesh. So Professor Salam has a long profile as well. So I would not spend a lot of time to introduce so much, but certainly his profile is, at the moment, I just realized he has been a key person out there at the University of Dhaka as the Pro-Vice Chancellor after he has been the Dean. And the most important thing for us at the moment is that he has been leading the observatory out there in Bhopal and also in the urban of Bangladesh, a huge research team. Also, he has collaboration with many countries. But for this moment, we will hear from him about the Bhopal, mainly the climate observatory. So you want me to share your slide, right?
Yes, please. Can you see my slide?
Sure, I'm going to do that at a moment. Can everyone see this? Is it on the full screen now?
Yes. So I shared or you shared?
If you can share, it's okay. But now I'm sharing. Yeah.
Okay. So I can start now.
Yes, please.
Thank you, Vanessa, to invite me here to give a presentation. Actually, I will try to speak on overall air quality stuffs in Bangladesh and as well as some rural areas, especially in Bhola. So it's not a Bhopal, it's Bhola. First, I would like to correct it. It's Bhola Island. And thanks to Professor Orion for his excellent presentation, and he also covered many things from BCOV observatory. And today I will try to speak on long-term observation, and I have many collaborators already written in the bottom. Next slide, please. Overview of Bangladesh is maybe many of you knows Bangladesh is a Southeast Asian country with very high population density, about 200 million people living very tiny area like 147 square kilometers, and our economy is transferring from agriculture to industry. So industry produces a lot of pollution. That's impact on our country. And Dhaka is the capital and very fast growing city, but very unplanned way too. And in sometimes the PM 2.5 concentration goes up to 100 times higher than WHO guideline below. And Bangladesh face serious health risk problem due to the poor air quality, and life expectancy reduced 5 to 6 years. Whole Bangladesh, especially in Dhaka, it goes up to 8 years. And the economic impact of air pollution is also substantial. You know, Bangladesh is a developing country. So about 7.5% of its GDP, which is equivalent to $21 billion goes for air pollution cost. I mean, different disease and others for the human being. And next, you see the one picture on the left. Dhaka city is like this. A lot of animals, especially deer, and it's like trees and free land. But nowadays, Dhaka city is like right hand side pictures. Everywhere is concrete building and building. And every so frequent, you will see many news in the newspaper like Dhaka air quality is worsen again, and Dhaka most polluted city in the world. This kind of news in the media. This is due to the pollution every year in Dhaka city. Can you go next? This slide shows, you know, the people died in Bangladesh every year. 26% is died due to the environmental problem, and 75% of this 26% are due to the air pollutions. So there are many diseases, you know, COPD, brain stroke, and heart stroke, diabetic, a lot of diseases related to the air pollution. And Bangladesh is the #1 due to the death for the environmental pollution. Next, please. Next, please. And there are many sources contribute to the poor air quality in Bangladesh. Vehicular emission, you know, a lot of traffic jam, and also construction activities due to it's a developing country, a lot of construction happening, and road dust and indoor cooking. You know, we use biomass, especially in the rural areas for cooking. That's also produce a lot of pollution. And in Bangladesh, there are about 12,000 brick kilns. In and around Dhaka, Greater Dhaka region, there are about 800 brick kilns. So they use normally coal. This also produces a lot of pollution, and garbage burning emission. And most important one is transboundary pollution. And due to the geographical location, during winter time, about 40% pollution in Dhaka or in Bangladesh is coming from neighboring countries. So we have a lot of pollution, and we are getting a lot of pollution from outside of Bangladesh. So that's also serious issues for Bangladesh. And I mentioned already traffic pollution, you know, huge jam. We have one road and it has pollution, and we build 2 straight roads. Still there are a lot of traffic jam, and that produces a lot of pollution. You know, I think last couple of years back, there is a ranking. Dhaka is the highest traffic jam in the world. So the situation is not so good in Dhaka city, or that contribute to the overall Bangladesh. Next one. And another important source is brick kilns. I already mentioned brick kilns. They use their main fuel is coal. and sometimes they also burn woods. So that produce really huge pollution. And there are many technologies, zigzag, tunnel, and FCK. And the old is one is FCK, and that phase out. But still, there are some FCK brick-kilns in Bangladesh, and tunnel, zigzag, all are good, technologically good, but it still produces a lot of pollution. And our government taking steps to phase out, but it's not yet successfully happened. And the next one is I mentioned about indoor biomass burning. Mostly the women are used to cook in their home, and they use biomass burning, and that produces a lot of haze, smoke inside the kitchen. And there is also one of the solution, the smoke goes outside, but still that also contribute to the air pollution. There is another important source is garbage burning. There is not so much work in Bangladesh about the garbage burning emission, but there is one manuscript from India and Nepal. They contribute about 25% of the total PM 2.5 from garbage burning emissions. So Dhaka or Bangladesh garbage burning is also another important sources to contribute air pollution. Next one. And this is most important, the unplanned and uncontrolled constructions. It is happening almost around the year. One agency did this and they closed it, and another agency came and also they did the same thing. So that's also produced a lot of pollution. The next one is transboundary air pollution. You see, the right-hand side picture is from satellite image. All the boundaries covered by haze. And if you see left-hand side figure, the air mass coming from our neighboring countries to Bangladesh, and also the pre-monsoon time is coming from the ocean, and winter is coming from the neighboring countries. So during the pre-monsoon and monsoon time, we have less pollution. There are many reasons actually. One of the reasons is transboundary pollution. As other reason is there are many industries that are not operating during monsoon time. For example, brick kiln, rice parboil industry. And also there are a lot of rain during the monsoon time that reduces air pollution, wash out the pollution. If you see the picture, about 75% air mass coming during winter time from the north and northwest. And we have working in a measuring air pollution, and we have also set up in two location in Bangladesh. One is the capital Dhaka city, another one is the near the Bay of Bengal. Just you mentioned is the Bola Observatory, and Orion also mentioned many times. We have all the instruments there for measuring both super pollutant and also regular PM 2.5 and others. Next one. This is the Bola Observatory. It's about 1 square kilometer agricultural field. It is middle of the field, so there is not so much local emission. And the nearby road, there is some traffic, but there is no industry at all. But definitely there are some influences from the local cooking. And we have everything for in this observatory for measuring air quality, both super pollutant also and other stuffs too. And in the picture, you can see one of our colleagues from Stockholm University, Henry, fixing some instrument for carbon monoxide, carbon dioxide, and others. And the bottom one is the PM 2.5 measuring device, is digital device, high volume sampler. Next. And if you see during the harvesting time, this looks like this picture. You have another one, Melissa. Oh, Orion shows this picture too. This is the part of South Asian pollution experiment. We started measuring basically 2013, about 30 years already gone. from these observatories. So we have a lot of data, and we already published many papers from this observatory with the collaboration of Stockholm University mainly, and there are some other collaborators to NASA and also other US and European agencies, especially University of Bristol, also contributing and collaborating in this observatory. Next one. And both the observatories, both Dhaka and Bola, we also have long-term monitoring for both aerosol optical depth with the CML sunphotometer, NASA Aeronet, part of NASA Aeronet project. And we also have Pandora spectrophotometer measuring in Dhaka city for all the gases like sulfur dioxide, nitrogen, nitrogen dioxide, ozone, and formaldehyde. But NASA Pandora is a relatively new, but Aeronet for aerosol optical that we are measuring also about more than 12 years in both the location in Dhaka and also Bola. Next. And this is, we have another collaboration is also in Dhaka, is called Spartan. And it has 17 locations in all over the world. And we use air photon devices for measuring PM 2.5. And we can do it very automatic. And we measure for all kind of pollution like heavy metals, black carbon and organic carbon, and also sulfate nitrate. But this we measure in only in Dhaka city. Next one, we also have a monitoring network for local sensor. In the left-hand side, you can see we have a network from Pakistan, India, Nepal, Bangladesh, Sri Lanka, and also Maldives. And we have about 70 local sensor installed all over Bangladesh. And in Dhaka city, we have about 40 local sensor installed for measuring PM 2.5 and so on. So, and we, for local sensor, we actually calibrated that with a graded instrument like BAM devices. And after that, we also do some kind of calculation and harmonize the data, but they also give the pretty good data. Next. And from this figure, you can see the PM 2.5 concentration and almost 10 years. So you see every year there is a two peak. One is the monsoon below and winter is very high. And this is for three locations. One is Dhaka, two is from Dhaka and one is from Kolkata, but their nature and behavior almost same. Just every year it goes up during winter time, and in summertime it goes down. And so this is, and even the monsoon time is also much higher than WHO guideline below. Next. And if we see the monthly variation like January, February, March, April, May, June, July, August, September, October, November, and December in the x-axis, you see June, July, August during the monsoon time, the concentration is really low, but even much higher than WHO. And January, February, December is really very, very high. And from pre-monsoon and monsoon, post-monsoon, they are in between. But there is not so many cases below WHO guideline below. Next. And also the same situation for the gaseous pollutant, especially you mentioned super pollutant, carbon monoxide, ozone, nitrogen dioxide, and sulfur dioxide. We see about 10 years trend, and always it goes up and up. And they also follow the seasonal pattern like other PM 2.5 and also AOD. And except the ozone, you know, ozone is the secondary pollutant. So they have different behavior, but sulfur dioxide, nitrogen dioxide, and carbon monoxide, they have increasing trend and also a strong seasonal variation. Next. And this is our sensor result. If you see the sensor also, local sensor also give the similar result like our graded instrument. They also show the June, July, August is low, and January, February, and January, February, and also December, November, they are very high pollution. And we also, the bottom two is for the their variation with our graded instrument and also local sensor PM 2.5. Next one. This is one of the important things, I think, especially in Delhi and Dhaka. The pollution level even much higher during nighttime compared to daytime. And we have 6 or 7 different locations, and we found every time the pollution is much higher during nighttime than daytime, especially 3 p.m. They have minimum value, and during nighttime is going up and up. And we also have the similar picture by filter-based measurement. You see the nighttime one is the really dark one, and daytime is also dark, but relatively less dark. So the pollution in Dhaka during nighttime is much higher than during daytime. Next. And also we have see the similar pattern from aerosol optical depth. The June, July, August has the lowest, and January, February, March is higher pollution than the monsoon time. So I think all of them have the different values, but message is same. Our winter time pollution is much higher, and monsoon time is relatively lower. Whatever the measurement from low cost and also graded instrument, or it is aerosol optical depth. Next. This is the overall situation in Bangladesh. If we see from satellite data, mirror to MODIS Terra, and all shows the whole Bangladesh is kind of under high pollution coverage. Only few part on the east and northern east and north side, only a small area you see the green, but most of the location in Bangladesh is always very high pollution coverage. Next one. And if we see the aerosol optical depth over Bangladesh, and we can classify in 4 different seasons, and the type is like anthropogenic and biomass, and also mixed type pollutions, and it's slightly different among season, but mostly anthropogenic and biomass emission contribute significantly to the aerosol optical depth in Bangladesh. And this is chemical. Next slide, please. Next one.
Chemical composition?
No, next one. Okay. This is one of the interesting slide for, from a Spartan result. We see the elemental composition, especially heavy metals, and Dhaka and many other regions of the world. Most of the cases, our pollution level is really high, and our pollution level is very high, especially if you see the lead and also arsenic. And you see in the bottom line, Dhaka is like 1100 nanogram per meter cube, and other regions, some area you see 6 nanogram per meter cube, and the WHO guideline below is like 500. So there was a lead pollution over Bangladesh, and lead-free gasoline was introduced. After that, it goes down, but now again it goes up due to leaded, there are some battery operated rickshaws, so that also contributes significantly in lead, and arsenic also relatively higher value due to the dust, because our dust also contain relatively higher arsenic that comes from the groundwater. Next one, please. What I meant see the comparison between different location of the world. I already mentioned the arsenic concentration in Dhaka is very high, and also PM 2.5 concentration, if you see, is the kind of third. So all the location in a Spartan side, Dhaka is relatively higher or the highest pollution, especially for metal content. Next one, please. Please, next one. Yeah, we have a brick kilns emission I mentioned, and we the middle map shows the location of bricks, the red point you can see in and around Dhaka city, about 1,000 brick kilns, and we sample 18 brick kilns, and we measure different technology brick kilns too, and our result shows that FCK, fixed chimney kiln, fixed kiln chimney, and zigzag, and also Hoffman hybrid kilns, and they all produce pollution, but the tunnel kiln is the relatively lower pollution. So brick kiln has a significant emission to the atmospheric pollution in Dhaka. There is one recent article published in Science, but not from our group. They also shows reducing emission and air pollution from brick kilns in Dhaka, in Bangladesh especially. Next one, please. Next one, please. Next one. Next one. Yeah, okay. This is one of the result. Orion is the also author, and we measure it's during I think 2013 or 14 during a strike in Dhaka, and we found very interesting result. Biomass is equivalent contributor to the black carbon in Dhaka. But before that, we thought maybe traffic pollution is the major source. But we see traffic and biomass are equally contribute to the black carbon emission in Bangladesh. Next one, please. Next one, please. I think I have not enough time. I have to leave. This is one of the interesting slides. You see the leaves of the plant, how dirty these are. There are a lot of dust in the atmosphere, and they stay on the leaves. And we collect those leaves, and we try to measure their air pollution tolerance index based of the following chemical component, like total chlorophyll content, ascorbic acid, and water content, and pH determination, and put this equation, and we calculate the air pollution tolerance index, and we found there are some plants are good in dirty environment, and some plants are not good in dirty environment. Next one, please. And we found that the chemical composition values is highly correlated with the PM 2.5 concentration. When PM 2.5 concentration is high, their APTI is low, and also other parameter is, for example, total organic carbon and ascorbic acid concentration also gradually shows with a correlation with APTI values. Next one, please. Next one, please. I will not speak on this. This is another important slide I'd like to share. The plastic emission. Couple of years back, we measure 1,3,5-triphenyl benzene, which that is one of the tracer for plastic burning. And we found, you see, the top one is Dhaka, Bangladesh, and which is 10 times or even more higher than other locations in Nepal and also USA. And we also collect sample in Bola, but there is not mass 1,3,5-triphenyl benzene. So we can say Dhaka has a lot of plastic burning pollution in Dhaka atmosphere compared to rural Bangladesh and also other locations of the world. Next one, please. In the next couple of slides, I would like to show actually the particulate matter exposure to the residents in different location. So our findings is when PM 2.5 is concentration is higher, the lung efficiency of the resident of the homes is lower, because when particles is higher, they block the alveoli. Also they have some diseases among the resident, for example, COPD. So that impact on their lung efficiency. And we found PM 2.5, especially ultrafine particles, PM 2.5 and PM1 is highly correlated with their lung function compromise. And this is also same personal exposure at different micro environments, PM 2.5, and we found there are a lot of areas when activities going on and the personal exposure is higher for PM 2.5, and different microenvironment shows different kind of personal exposure of pollution. Next one. This is also very interesting. We did a study about 10 school, and we found that about 50 to 60% school students they have lung function problem. Due to the pollution, their ability for lung function reduced, and we did it the very simple device like peak flow meter, and there is some value that gives standard, but we found due to the pollution the lung function efficiency of the students highly compromised. Next one. And this is one of the study we did in hospital environment, and we calculate the toxicity potential. People visit hospital, to become cured, but the environment inside the hospital is also not good, and we found toxicity potential is 10 times higher than normal. So this is also negative impact on the patient, those who are admitted in the hospital. Next one. Finally, I would like to conclude my slides. What actually we need to do. Challenges to air quality management in Bangladesh, or especially in Dhaka. Weak enforcement capacity, definitely. Rapid urbanization and informal sectoral growth, and limited regional coordination, lack of public awareness. These are the challenges. And our recommendation is enforce emission standard for vehicle and industries, promote clean energy and public transportation, regulate construction, and also promote green infrastructure, and definitely funding and institutional capacity for air quality management is an important thing, and extend regional collaboration for transboundary air pollution. And finally, conclusion is urgent, multi-sectoral action needed, health and economy at stake, and a clean environment is essential for sustainable development, not only in Bangladesh, all over the world. Next one.
Oh,
Next
sorry,
slide.
sorry. I should
Next
share
slide.
that. Okay, just
Okay, in next slides, I would like to show a lot of my collaborators. Our facilities are also limited, so we always depend on our collaborators. And Professor Orion Gustafsson is one of our great long-time collaborators. In Stockholm University, there are some other collaborators also, like NASA and Spartan and University of Bristol. They are our main collaborators. So thank you all. I made some hurry, I have to join our Senate meeting just at 3. So sorry, and thank you all.
okay, thank you so much, Professor Abdul Salam, for this detailed description regarding your current findings in Bangladesh. We have quick question. Can I ask? It's not yet posted, but it was sent beforehand by the participant when they register. There's a question from actually an engineer in Bangladesh. I'm not sure he's joining now. Mr. Asifu Buyan. He mentioned in South Asia, especially Bangladesh, same job and different companies are here. This like accelerate the pollution. So how to check about the current situation of the pollution, I think.
Oh, the current system, there are many ways you can check pollution level. You can go to the air visual website. You can check the current air quality status, and also in some areas from the government, they put some kind of skin that shows the PM 2.5 level, black carbon level, and others. So they can closely observe that skin, and also they can go to the website Air Visual and many other websites. They give the current situation of the air pollution. Even also DOE, Department of Environment, they have a website you can go there and also see the air quality status. They made it, I think, based on 5 different pollutant, PM 2.5 and sulfur dioxide, PM, and also hydrocarbon basis. They put in their website, so they can visit website, many website, and also on the scheme. Thank you.
Okay, thank you so much. And if there are no more other questions, I will move on to the last speaker. And once again, thank you, Professor Abdul Salam. If anyone have question, can send in, and we will relay to, because I think Professor Salam is have to leave, right? At the moment,
Yes.
he has another meeting. So once again, thanks a lot. And I move on to the last speaker is Associate Professor Krishnakant Buddhavan, who actually has been the scientist, the key resident scientist in Hanimadu in the Maldives. And the MCOH, as you have already has been mentioned by the first speaker, but more details, I think, as he has been also a full-time professor at the Divesha Center for Climate Change in Bengaluru, India as well. So without wasting much time, actually the profile has been shared out there for his background. So I want to pass on the microphone to Dr. Krishnakant, please. Thank you very much.
First of all, I'll share my presentation.
Yes, please.
Can you see my slide now? Presentation slide?
Yes, it's there. Yes, you can start.
Okay, is it in full mode? Presentation mode?
It's good, full screen. Thank you very much.
Okay. Good afternoon, everyone. And first of all, thank you, organizer, for giving us invitations to present in the Mala Declaration webinar series. It is a great pleasure and have opportunity to share some of our scientific advances from MCOH to discuss how long-term atmospheric observations are improving the understanding of superpollutant or South Asia and Indian Ocean. Professor Gustafsson and some extent Professor Salam has already covered and give some background about MCOH. So I'm not spending more time on that. So I will start presentations with explaining about MCOH. It is inaugurated in 2004 after the Indo-X program, where that is actually conducted over Indian Ocean and Arabian Sea. So where they found like a polluted haze or kind of clouds, brown color clouds forming over Indian Oceans, and that's they gave an Asian brown cloud names, and later they changed. They found like a kind of clouds other part of the world, so they given atmospheric brown clouds. So on the basis of that, this observatory established in Maldives in 2004. So initially it is led by Professor V. Ramanathan and Nobel laureate Professor Paul Kodson with the help also Professor Henning Rode from Stockholm University. And they started the observations, and later on, since 2011, under the guidance of Professor Gustafsson and teams, we are continuing these observations. Like we have almost 2 decades of long-term observations. So it gets it's not possible because of this solid international collaboration as well as the local support from Maldives government. So there are many international partners, but currently now I'm more focusing on recent studies and collaborations. So we can see here, like there are many international collaborated, mainly led by Stockholm University, NASA Aeronet program, Maldives Meteorological Service, Indian Institute of Science, IITM Bangalore, University of Dhaka, University of Bristol, Finnish Meteorology Institutes, and Screen Institute of Oceanography. So there are all those international partners. So that makes us easy to sustain and contain such a long-term observations at MCOH. So we have like observations like more than 20 years. We have so far publications like around 40 publications from MCOH. And before starting actual results, I will give some like overview of infrastructures at MCOH. We have world-class observations, some like instruments, and we conduct quality checks and all. So if you see this left side, you can see the tower where we do the mostly our measurements, like aerosol filter measurements, solar radiation measurements, as well as we measure the meteorological data. Precipitation collector is installed there to measure the rain chemistry. There are several passive samplers. Also, you can see right side that also that is in the lab where it is lab is connected with the 20 meter, it's like a 15-meter inlet, which is attached to the tower here in the left side. So you can see with that inlet, we used to get all this air to the labs where we continuously operate instruments, mostly like athylometers, nephelometers, size distribution aerosols, like size distribution measurements of we do that with that inlets, and also we do some gas measurements with that inlets. You can see the center like a picture of the beautiful climate observatory, as well as some facilities at observatory. Here coming to the scientific contributions to the MCOH, you can see like since 2004 to 2026, we have more than 40 publications. So that publications I broadly categorize in the black carbon sources and fingerprints, which is led by initially Professor Gustafsson in science. Later on, we continued that legacy, and then later like aerosols optical properties we measure with the different instruments. We studied the brown carbon and its climate forcing. They're also published in world standards journals, high impact journals. Then we also do the greenhouse gases, sulfate chemistry, organic aerosols, molecular compositions. All these different groups I categorize into different publications. These publications also happens due to like a large international campus. Actually, MCOH host big international campus like atmospheric brown clouds, Cardex, EPIMAX, and currently we are continuing the SAPOEX, South Asian pollution experiments. So you can see here down like 2004 to 2026. These are like I'm just focusing on super pollutants like black carbon, brown carbon, sulfate, and other aerosols. So these are these highlights during these years. Actually going to the research journey means like actually this scientific discoveries I categorize, my presentations I categorize into 4 parts. First, I will discuss about and how this aerosols transport happen. It's like MCOH receives air during winter time mostly from South Asia, but monsoon time it's also cover air mostly traveling from the Indian Ocean as well as Africa. So we can see that first one, transport. Then once we know the transport, like then we have to like say source to receptor regions, like a lot of thousands of kilometers the air pollution is traveling. So there is kind of a lot of processes and aging is happening during that time. So that also here I try to explain it. And after coming the aerosols, like what kind of sources, where that sources comes. So that I put in the third part, and how that results, like this long-term results help to the climate implications and molar improvement. You can see the right side like a roadmap or like my presentation. So let's start with the, like especially during the winter time. If you can see the first graph, most of this years mostly comes from South Asia and mainly from Indo-Gangetic Plain. So whatever the aerosols comes to the MCH during especially winter time, like December to March, it's mainly dominated by the polluted air from IGP, Indo-Gangetic Plains. So this is one of the polluted regions in South Asia. So in that, when with the help of back trajectories and other calculations, we found like mainly all these particles are fine particles. The coarse particle contribution is very compared to less. And here we see like 97% of black carbon, mostly we found in the PM2.5. And also like other aerosols like organic carbon sulfate, ammonia, potassiums. Also we found in the fine mode. So these studies you can see in the center middle, mostly these fine particles colored with the red, and the third figure you can see left right hand side. So these are mostly like traces like potassiums, ICOC ratios that will give the indication of sources. So we can see that is kind of primary combustion sources are dominated during this transport. So the next question comes like once they emits in the atmosphere, is there any meteorological factors affecting? Generally, answer we should be yes, because it interacted with the clouds and precipitations with these. So the next studies, which is led by the Guest et al., it shows like more than like a 5 to 6 years observations with the help of DMPS and SMPS. First figure you can see the dominant floor from South Asia from IGP, and down one like left side figures was during monsoon times wind mostly travels to the Indian Oceans, Australia and African part. So there is a kind of precipitations is taking major role to control this scavenging of aerosols. Particularly if you see that center graph, mostly 100 to 300 nanometer particles like which is comes in accumulations mode are affecting due to the precipitations. And also you can see the like right side graph number and size distribution. So there we can say that is in bimodal. We can see that is definitely that accumulation aerosols are affecting by the precipitations. So with these two publications, we know the how from where this polluted air comes, what are the meteorological factors are affecting them. So next question comes like how this, what are the sources of that? So to find that one, we conducted again several studies. Like first, this is Professor Orion already covered the time during the winter time. So I will focus on monsoon here. So this is the first isotopes constant investigation BC during South Asian monsoon happens. Like this is 5 years period. You can see the left side with the help of stable isotopes carbon-13 and radioisotope carbon-14. We separated the source like mostly here and during monsoon time, mostly winds comes from Indian Ocean as well as from Africa. So that is kind of 65% of fossil fuel is dominated, which is opposite to the when the where comes from South Asia, where contributions from fossil fuel is 50 and 50 fossil fuel and biomass contributions. So which is kind of different during the southwest monsoon. Here in this we noted that one. It is published in PNS, and also you can see in the center figure you can see the mass absorption coefficient. This is the main important parameters mostly used in the models to estimate radiative forcing and there. Here we found like mostly during the southwest monsoon we found more edge aerosols compared to the winter time aerosols. And if you see the source apportionment in the first, again, go to the first the figure. So African, like there is, if you see the 2D model, we can see the some of this the African fires are contributed to this rate trajectories that we can see, like sometimes it reached like up to 48% is affected by the savanna fires. We can see that was again in the third slides where using Monte Carlo simulations, we estimated like how much C3 and C4 plants are contributed. So there is kind of, we can clearly see that C4 plants are affecting during that period, and which is mostly possible only from African fires. This study also suggests like there is a kind of long distance between MCOH and Africa. So that is kinds of thousands of kilometers the BC travel, and maybe based on the based on our back trajectories, we estimated like black carbon time in the atmosphere more than 2 weeks. This also highlighted in these studies. So the next questions comes like now we talked about black carbon. Next questions like how the black carbon is like brown carbons. So again, coming to the winter time, they did these studies in 2019. Sorry, 2000. I was part of SOPOEX 16 program. So we conducted observations for Delhi BCOB means Bangladesh, or the Bolaba Climate Observatory, and you can see the left sides again MCOH, that is placed on Northern Indian Ocean. So this is we did observation during synoptic period, mostly, which means the period which is dominated by the IGP flow. So we estimated like here. The pollution travels from Delhi to BCOB and MCOH, particularly brown carbon. It's a kind of, it's changing like by its properties, like some of this brown carbon is highly sensitive to absorb sunlight. So this is very important. If you see the Delhi BCOB and MCOH, and the right side, you can see that it is kind of losing the absorption property. It is a bit because we can say that it's because of photochemical bleaching, and the rate we calculated is from Delhi to MCOH is like 0.2 per like 0.05 per day. So this is also one of these first studies for South Asia. We reported this one. So here we can say that the key findings like fresh brown carbons, it absorbs more strong near the source region, but once it is get in the atmosphere and transport for photo oxidations, progressively transport the brown carbon and reduce it's almost like 84% reduction in the light absorbing capacity. So this also need to count in the models. Now coming to the next slides. Now we discuss both like a brown carbon and black carbon. But when we try to keep together and you want to study it together, how this behavior. So we came with another study here, like which is published in ACP in 2024, where we found like we conducted like BCOB as a source and MCOH, and one more observatory we are operating at near on the equator. We can say GAN, Maldives Climate Observatory at GAN. So this is kind of almost 2,000 to 3,000 kilometers. So we did observations parallelly there and considered the BCOB as a source. We found like a BC absorption capacity is increasing like more than 80%. But at the similar time, brown carbon also is decreasing its absorptivity like it's almost 3 times. So this is also kind of first study happen, first regional evidence contrasting, which gives the BC and black carbon and brown carbon has different optical properties. And this also need to consider in the models, climate models. So the next, again, coming to the black carbon, when it is kind of dry or wet form, we can see that we have already studied the properties during when the particles aerosols are dry. But when it is in the rain or in the clouds, is there any chances like a changing optical properties of the black carbon? And for this we studied the rain chemistry and with the rainwater and parallelly connected conducted aerosol samples. If you see the left side again, this is broader arrows which represent a seasonal air masses like a southwest monsoon. We can see then in the yellow, and northeast monsoon, we can see in the red. And center figure, you can see the left sides again, like insoluble organic carbon, BC MAC. Also, it is in the dry mode, and if you see in the blue color, it is in the wet form. It's the particles we collected in the rain, which is filtered with the QMA filters, and we measure the black carbon from that. So we found like MAC in the rainwater is almost double than measured in the aerosols. So this is also like one of the first studies from not only South Asia but other part of the world, where we showed like when the black carbon present in the clouds, or it may have larger impact than the air. You can also see that left side, that's the third graph. You can see the fluxes we calculated. So we see that it's rain not only precipitation not only remove the aerosols, but is also like edge aerosols, so also it is removing. So basically, we used isotopes methods to find out like robust methods, which is differentiate with the fossil and biomass burning using isotope studies. So similar, we used isotopes techniques to study that sulfate isotope. So next super pollutants like sulfate isotopes. So this papers also this year published, and which shows that sulfate or MCOH, it is mostly from anthropogenic sources. Again, if you see in first figures, there is a end members like anthropogenic and DMS, like dimethyl sulfate. These are the two. Based on these members, we found like winter time aerosols, like winter time sulfate aerosols, which is almost contribution 93%. Compared to the spring 87%, and summer monsoon it is like 66%. So it's a kind of all the years we can see sulfate anthropogenic source of sulfate is dominating at MCOH. And again, we try to see how these aerosols are connected with the other aerosols. Like when we see the relations with the black carbon, we found like a very strong correlations with the black carbon and sulfate, which is again you see the delta carbon 13 port versus carbon 14 radioisotopes. There we found a very strong relations. So we can here say that it is they are from the same sources. So this is kind of stable isotope studies reveals that anthropogenic emissions now dominate sulfate aerosols throughout the year, producing like a first robust observation constraint to improve the regional climate and air quality models. So we do the same things here, like in the gases also, like Professor Gustafsson already explained the figures, but I'm not going to more details. So here we can see we have like a left side again South Asia, mostly in India. We have conducted we collected samples from different sources, and based on the sources, we found out like what are the major sources, because if you see overall world compare, like 1/3 of global happening due to the methane. But most of these measurements based on these studies happens for Europe and US, but no, it is not happen in the South Asian continent. So this is kind of first studies where we can separate it. We can give the information about sources, like 4 major sources, like biomass burning, ruminants, rice paddies, and wastewaters. So based on this, we'll get idea like about the methane in the South Asia. So now this is like a second part is finished. Now I'm going to the third part, where like how this observations at so long-term observations connected with the climate, first of the, and this we can get the idea during the COVID-19 times, where we consider, for example, this COVID-19 give opportunity to slow down this community activities and all. So that is kind of during COVID activity, we found most of these places, or South Asia and other part of, like it is large reduce in the emission and pollution levels. So we found, like if you see again here, like a left-handed side, before COVID and after COVID, and see the last Mr. First figure, third panel, you can see the difference. This is we can see with the help of satellite pictures, but we did say similar kind of ground-based evidence. We collected the samples during the COVID at MCH. We found like a super pollutant like black carbon, black carbon and other particles are drastically reduced at MCH. Also, like aerosol optical depth, which is also indicated of pollution. So there is a drop in the AOD also, and obviously there is the particle numbers also we have seen that. So this is the kind of ground-based evidence when we during the COVID time. So this is kind of, if you see this one, like interesting things here, this pollutant and AOD decreases, but the incoming solar radiation is increasing during this time. So this is, if you see the number wise, these observations indicated aerosol decreases up to 40% across all South Asia, but increasing solar radiation increased by the 7%. It means increasing solar radiation means it's kind of surface brightening. It is kind of chances to increase the temperature. So when we put this in the radiative forcing, we found like aerosol demasking produced 1.4 watt per meter square additional regional forcing. So this is kind of, these observations provide first observational constraint to aerosol masking, improve the future climate projections and migration strategy, because only reducing pollution is not straightforward pollution. We also need to think about the greenhouse gases. And also now next slide, this is like the example we found like when there's aerosols and when there are not aerosols. Next also this long-term observations, we also try to estimate like already Professor Gustafsson's already explained many things about black carbon. So one of the parameters is a lifetime. So based on Jingu-Japson methods and this with the help of like atmospheric black carbon and CO measurement at MCH, like a 3 years period, we used inverse modeling techniques to estimate this lifetime of black carbon in the over this Maldives. So we found like a lifetime of black carbon is 8 days, which is kind of slightly higher than not highly, almost 45% longer than model predicted. So this is kind of again the evidence from comes from MCH, and this MCH observations, that's why very useful and scientifically it's valid observations can give the values to the models, so they can improve the model forecast, or you can say that results. So this is kind of, I selected so far like a 10 publications, recent publication. I can say that like there is kind of 40 plus publications. It's not possible for me to explain each and every publication, but here whatever 10 publications I presented here, that gives like this, I will give the presentations like how this observations are helpful, because this is kind of established benchmark observation of South Asia aerosol transport, reveal contrasting aerosol aging of black carbon and brown carbon. So we applied isotopes techniques for aerosols and methane sources to find the other sources. We also improved the estimate of black carbon emissions and its lifetimes, just I discussed, and provided observational constraint for regional climate models. And that's why like a connected atmospheric science and with the evidence-based environment policy, that is only happened because of the MCH observations, like almost more than 20 years observations. So this is what I can conclude here. You can see in the picture format, also graphical format to understand easily. Then again, coming to the like these 40 publications are not only published like a regular scientific journals. It's published like a very high impact journals like Nature Review, Communication, NPJ, Science, PNS, ASAP. So this is kind of great contribution from different scientists involved in this project, and there are we are doing like as we are trying as best contribute to this maintaining the observations and quality measurements. So not only we have published these papers in the journals, but that also like helpful to the we provide to the policymakers in the different reports. Actually, this slide is already covered by Professor Gustafsson, so I'm not going to discuss these things. So I'm coming to my conclusion side, next slides, where we can see this like a MSUH receives around of the like airs from South Asia, Middle East, and East Asia. So there is kind of different kind of field campaigns with the different objectives we can conduct it. Since this observation, this webinar is focused on super pollutant, I covered only super pollutant things, but there are like many other studies are focusing with the different objectives. So where we do this measurement. So we can see so far like this is a very strategic locations and only one observatory in Indian Oceans that gives that long-term time series data. So this is kind of, again, this is a natural observatory laboratory to linking the atmospheric observations and climate science and policymakers. So basically what we do that there at MCUH, we do the measurements, reports, and do the verifications. And that's it. I said like thank you for listening, and I'm happy to answer the questions.
Okay, thank you so much for your presentation that has already given a number of good suggestion and conclusion. And there have been actually so limit of time. I'm so sorry that I think we delayed pretty much on the program, and we have only 5 minutes left. But I don't know if anyone has some particular questions right now. I don't see in the Q&A box at all. I think because of this program, we have had a number of good, most of the people attending a number of different webinar and also conferences at this day. So we have maybe people will send in more of the questions afterwards as well. So thank you so much for the indication you have given, and that will be a very good input to our declaration program. Thank you so much, Dr. Krishnakant. And I think for the last, very, very last but not least, yes, we would like to ask for the closing remarks from our colleague from UNEP, Ms. Yoo Jeong Kim. Yes, I'm so sorry if I allow so little time, but certainly if you can give us, you can also indicate something to our speakers and also sending in the message for us. Thank you so much.
Thank you, Professor Vanessa, and good afternoon, colleagues. It's my great pleasure to give you a few remarks on behalf of UN Environment Program. So first of all, big congratulations to SACEP and AIT and its Regional Resource Center for Asia Pacific for a very timely and thought-provoking webinar today. And I would like to also express my sincere appreciation to our distinguished speakers and participants. So these discussions are especially relevant for our region, which continues to be at the forefront of the fight against air pollution. High levels of pollution affect human health, agricultural yields, ecosystems, and economic productivity, while also infringing on the human rights to a clean, healthy, and sustainable environment. Yet, as you know, investment for air quality remains far from sufficient, and this gap is particularly concerning because the urgency for action has never been greater. Environmental risks are no longer perceived as a long-term risk, but as an urgent daily reality for millions across the world. So in this context, and with many sustainable development goals off track in our region, it's essential to focus on integrated approaches that deliver multiple benefits. Action on air quality has been identified as one of these synergy solutions, because it can advance health, climate, food security, and sustainable development objectives at the same time. And this is exactly why the focus on super pollutants is so important. Air pollution and climate change are deeply interconnected, and many pollutants share common sources and solutions. Action on short-lived climate pollutants, including methane, black carbon, can deliver rapid benefits for climate, air quality, health, and food security, while complementing efforts to reduce CO2 emissions. So today's presentations have reinforced an important message. Superpollutants, particularly black carbon and ground-level ozone, are among the most critical challenges at the intersection of air quality, climate change, public health, food security, and sustainable development. Their impacts extend across national borders, making regional cooperation and scientific collaboration indispensable. At the same time, today's discussions have made it clear that sustaining this progress depends on robust and long-term monitoring systems. The observations presented today illustrate the immense value of sustained measurements in understanding trends, identifying sources, assessing long-range transport, and evaluating the effectiveness of policy interventions. Because these challenges are transboundary by nature, a coordinated regional approach will be essential for meaningful and transformative progress. At the 6th UN Environment Assembly in 2024, member states reaffirmed the need for stronger regional cooperation on air quality, with the adoption of resolution titled Promoting Regional Cooperation on Air Pollution to Improve Air Quality Globally. So in Asia and the Pacific, this cooperation is already supported by several important mechanisms and initiatives. For example, for close to 25 years, the Acid Deposition Monitoring Network in East Asia, EANET, has worked to create a common understanding of the state of atmospheric deposition and air pollution in East and Southeast Asia, provide inputs for decision-making, and promote cooperation. Integrated solutions have been a focus for the Asia-Pacific Clean Air Partnership, APCAP, and its partners developed a regional assessment which recommended 25 solutions that can deliver multiple benefits for air quality, public health, agriculture, and climate. UNEP is also a strong partner of ESCAP for the Asia-Pacific Regional Action Program on Air Pollution RAPAP. This is the first region-wide action program negotiated and agreed upon by governments. And on the nexus of air quality and health, UNEP is working closely with the WHO for the Asia-Pacific Regional Forum on Health and Environment. And building on these platforms, there's a need to further strengthen regional monitoring networks for black carbon, ozone, and other superpollutants across South Asia. And this includes enhancing measurement infrastructure, harmonizing monitoring methodologies, improving data sharing among countries, developing standardized emission inventories, and linking ground-based observations with satellite information analysis and forecasting tools. Long-term observations are essential, not only for advancing science, but also for providing the evidence base needed for informed policymaking and regional cooperation. So the Malé Declaration can play a central role in advancing this agenda. By working together, sharing data and expertise, and investing in scientific and institutional capacity, member countries can better understand transboundary pollution, strengthen source receptor assessments, and design effective solutions that deliver benefits for both people and the planet. So I hope that today's webinar will inspire continued dialogue, research, and cooperation on superpollutants across the region and help translate science into action and evidence into policy. So thank you very much for this webinar. I'll stop here.
Okay, thank you so much, Ms. Yu Jong Kim. I think you have linking up an answer. Actually, one question I have in mind when I listen to the talks also regarding that. The scientists have done very good work for a long time, more than decades, a few decades already. So we really need to address this. And as Professor Gustafsson already gave the conclusion also regarding that, we need a low-hanging fruit and need time for speed, right, in order to really get to 2030, achieving the goals, for example, at the SDG. I think there is a, thank you so much for taking your time to, I think there is a huge conference also at the moment at UNCC, where UNEP office in Bangkok is residing there, and we really appreciate that you taking time in this Mari Declaration, which has been recorded. And actually, it will also be shared today. Maybe we don't have too many participants, but a lot of people have already registered to receive the information afterwards. So I really appreciate UNEP that has been actually initial observation from Maldives in observatory in Maldives started also with the ABC program that Professor Gustafsson mentioned. I don't yet see any particular question, but I read one question that maybe as we should be closing today. A simple question from India, a participant sent in saying that in a day-to-day life, how to overcome a pollution with small steps. So I don't know if any speakers would like to say anything to answer this question. Actually, as one of the question that has been sent in from participants. Any tips or anything you want to say how to overcome maybe this pollution, because we see that it's very serious in India and other neighboring countries in South Asia. Yes, please. Or Professor Gustafsson.
There is not one silver bullet solution to this complex and wicked challenge. So I will refrain from giving any specific advice, but there is a lot of recipes out there, and I think the solutions come at all scales, from the individual that wants to contribute to, I think, nationwide legislation. I think we need to do a societal transformation. It's certainly not enough to know the science, but it's a centerpiece. It's not enough with technological solutions. We need them, but it's not enough by themselves. We need all sectors of society to work together in meeting this challenge, and it is happening. This transformation to sustainable society has that train has left the station a long time ago. It just goes a little bit too slow, that train of transformation, but it is happening. So we need to speed it up, and I think it happens at all scale. And I think it's important with the systemic shifts, where we implement different encouraging stimulus to move towards sustainable development. But there is certainly things one can do oneself as part of that, and one is, of course, to take interest in this and recognize that it will affect everyone, also ourselves.
Right.
So that's good motivation. May I take the opportunity to ask a question to Yu Jong Kim?
Okay. Yes.
First, I want to thank both Vanessa and your team at the AIT Leading Research Center and to UNEP for this sustained support for this effort. It's very important with institutional supports. And of course, I value the recognition of the importance of sustained measurements, because in an informed society, we want to lean on knowledge when we make decisions. And, measurements is what we can really lean on and trust very well. But my question is on the Sustainable Development Goals. They're up for revisions now, relatively soon. I think 2030. And while there is a Sustainable Development Goal for clean water, there isn't one for clean air. I wonder if if that is at all being discussed now in the revisions of the SDGs, that there ought to be one along the lines of clean air anyhow.
Well, thank you for the question. And just to answer the first one from the audience, I share the link to UNEP publication, Air Pollution in Asia and the Pacific, Science-Based Solutions. So I hope this publication will be helpful for you to support tackling the air pollution action here in the region. And to answer your question, Professor Gustafsson, yes, as you mentioned, in our current 17 SDGs, we don't have SDG, especially for the clean air, right? And I understand this is being discussed within our clean air communities for sure. It looks like it was a little bit late when the discussion for the SDGs and Agenda 2030 was kind of being shaped. But for the next round, it's I think it's becoming more and more important for our community to speak up and to put this agenda forward. But a lot is uncertain yet, how this post-2030 agenda will be discussed and will be shaped. So it'll be really important to speak to our member states and all relevant stakeholders on how important to act on this agenda clean air, and how many different co-benefits and synergies it can create when it comes to the interlinkages between clean air, climate, health, food, and many more.
Thank you.
Great. Thank you very much for both the question and the answers. I think it's something already in mind, me too, and also many audience, yes, with all this discussion. So, okay, I think it's worth the time that we have been sharing together this afternoon for Thailand, and morning and late morning already in Sweden, where we see as a great contributor for the good air, I think, in Asia for a long time, as I recognize as well, together with all the other Asian people here. And I would also like to thank again all the speakers. Actually 3 speakers, one already left. Professor Abdul Salam also, he has already another commitment that he has to be leaving early. And in particular now, UNDP and our long-term collaboration. And here in the Maldives Declaration, that I have got a lot of information that we will bring it back to the table, hopefully with the IG meeting, intergovernmental meeting coming up for the Maldives Declaration for the South Asian countries. And we highlight those information that we have got today to the South Asian Cooperative Environmental Program, SACEP, and therefore I highly appreciate all the speakers who put all the efforts to bring about the solutions and answers to these activities that should continue. Okay, so thanks also to all the participants, and you have already filled in the evaluation form, I hope, and we will continue with the next webinar. Certainly, maybe the focus will be also more on the policy, if not on the technical parts, but we will please be in touch. And we will send out the news of the next webinar and the next meeting. Also, I think there will be some good news also coming up with the observatories in South Asia soon later in the year. So we wait to hear from there. And so I would like to now. I think we close the webinar and hope to see you again, maybe sometimes in person as well. Okay, and please take care, and until then, see you. Thanks very much. ขอบคุณค่ะ Okay.
Bye.
Yes.
Thank
Bye-bye.
you.
Thank you.
Bye-bye.
Thanks a lot.